All right, moving on. Charles' law. Now, some of these gas laws might be familiar to you. I'm hoping that they are. This might not be the first time you're hearing about Charles' law. Charles' law looks at the relationship between volume and temperature. The volume of a gas at STP, standard temperature and pressure, is directly proportionate to the temperature of the gas. Now, in the last video, we mentioned that you're going to see a lot of this indirect, directly proportional relationships. A directly proportional relationship looks kind of like this. If I increase the temperature of a gas, I will increase the volume. In a directly proportional relationship, both variables change proportionate to each other. If I increase the temperature, I increase the volume. Opposite of Boyle's law, which was an indirect or inversely proportional relationship. If I increase the pressure, I decreased the volume, or vice versa. Okay, so like on a particle level, I think this makes sense. I think gas laws in general just kind of make sense because we've talked about gas behavior in general, that temperature is a measure of average kinetic energy. So as I increase the temperature, the particles have more kinetic energy, energy of movement. If there's more kinetic energy, there's more collisions. Now, one thing that has to happen for Charles' law to work is that I need to have a container that allows for expansion. The container needs to be able to change in volume. So an example might be like this, I don't know, piston setup thing we have here, where this movable piston can expand to allow the volume to increase. Or like a balloon. If I increase the temperature on a balloon, the gas particles inside will have more collisions with the walls of the balloon, and it allows for expansion. Now, the opposite is also true. I totally remember one time I was like, I don't know, in elementary school or something, and I remember going to like the party store to get balloons with my mom. We get the balloons in the car, it's like the middle of winter, and they all shrivel up. They look half deflated, which was probably like my feelings at that time because I was so excited for this birthday party. And it was just an early lesson in Charles' law. As soon as we brought the balloons back into the house where it was warm, they were totally fine. The gas particles expanded to fill out the volume of the balloon. But in the cold car, where the temperature had decreased and the kinetic energy of the gas particles decreased, well, there just weren't as many collisions and the volume decreased. Now again, in order for any of these little gas laws to hold true in the lab, there are some variables that we need to hold constant. So here are my constants. One constant, pressure. The external pressure needs to be the same. So in this little diagram, they're trying to show like there's the same amount of weight on each container. So for example, here's where this could fail. I increase the temperature, which would make me think that the container should expand, the gas particles would expand, leading to a larger volume. But if at the same time I also increase the pressure, now those variables like negate each other. Increasing the temperature would make the particles expand, but increasing the pressure would like smush, for lack of more scientific term, smush them into a smaller volume. So we have to study Charles' law at a constant external pressure. It also needs to be a closed container so that the number of particles is the same. So for example, again, if I have this container, but it's not like a tight seal and gas particles can somehow escape if there's a hole or whatever, well, then I could be increasing the temperature and I don't really see the volume expand because the particles are just escaping out of some kind of little pinhole. They're escaping through some kind of a leak. So when we study Charles' law in the lab, we have to have a tight seal on our equipment so that the number of particles is constant, and obviously the external atmospheric pressure would be constant. quantitatively, here is the equation that you'll be given to study Charles' law. I'm going to give this to you. Now you just have to know when to use it and how to use it. V1 over T1 equals V2 over T2. And again, like V1 and T1 are your initial conditions, your initial volume and temperature. V2, T2 are your final conditions. I remember that if it's a directly proportional relationship, the variables will be directly on top of each other in the little equation. For any set of conditions, if I take the volume and divide by the temperature, I should get a constant. And so I can set two sets of conditions equal to each other. There's just one little snafu, one little thing that we have to be aware of when we study Charles' law. Check out this graph. Pretty cute. Nice directly proportional relationship. As I increase the temperatures, the volumes steadily increase. So for example, at my highest temperatures, I have my highest volumes. At my lower temperatures, I have my lower volumes. Cool. Notice the units. Okay, so the volume was measured in milliliters, fine. The temperature. Oh, brother. What's this bad boy doing in there? Kelvin. In order for this relationship to truly work, your temperature must be measured in Kelvin, which is not a big deal. We can deal with this. Okay, so watch this. How do I know it's Charles' law? How do I know what equation to use, which is usually one of the most common questions I get? Look at the data set. A sample of neon gas at 50 degrees Celsius and volume of 2.5 liters is cooled to 25 degrees Celsius, and I want to know the new volume. So just look at your data set. I have degrees Celsius, which is obviously a temperature, and liters, which is obviously a volume. This is your Charles' law. This is going to be my equation of V1 over T1 equals V2 over T2. Now that's going to be given to you. So you don't have to remember, do I multiply, do I divide? I'll have that for you. The variables that you're looking for, volume. Either milliliters or liters. Either is fine. You don't have to switch them. As long as V1 and V2 are the same unit. Then it doesn't matter the unit as long as they're the same. But temperature is the one we have to be careful of. Temperature must be Kelvin. Must be Kelvin. So often in the lab we measure in Celsius. Our thermometers are Celsius thermometers. So you're going to need to do this. Take your Celsius and add 273 to get Kelvin. Hey, guess what? I'll give that to you as well. I'll put that on the test. I'll give it to you. I mean, again, if you were working in some lab and for whatever reason you forgot the conversion between Celsius and Kelvin, you just look it up, right? I'll give it to you. But you have to remember that it needs to be in Kelvin. Okay, so it's going to look like this. V1, T1 are my initial conditions. V1, my initial volume is the 2.5. Over T1. So in my calculator, I'm going to go 50 plus 273, which is 320. Okay, so I know you really, really want to do this, but you can't. And I'll tell you why in a minute. Not 50 degrees Celsius. It has to be Kelvin. Okay. There's my initial conditions. I want to know the new volume when the gas is cooled to 25 degrees Celsius. Okay, so V2 is my variable. And then I'm going to take 25 plus 273. And that is 298 Kelvin. Not 25 degrees Celsius. And I know it's really tempting. But you can't. Okay, so let's just plug this in. We're going to cross multiply. Then we're going to kind of do this and this. So in my calculator, I'm plugging in 298 times 2.5 divided by 323. Lovely. And my volume, my V2, is 2.3 liters. So the unit will stay the same. If the initial volume was liters, the final volume is liters. And for sig figs, I would just go with the initial. So the initial volume had 2 sig figs, so I'll leave 2 in my final volume. Okay, so let's see if this makes sense. We did decrease the temperature. So the particles have less kinetic energy, which means less collision, so yeah, less volume. It should be something less than 2.5. Not only should we be able to solve this mathematically, quantitatively, but we should also be able to explain these gas laws on a particle level. Why does the volume decrease or increase or whatever it might be? On a particle level, what's happening to the particles? Do they have more energy, less energy, more collisions, less collisions? Okay, so this 2.3 makes sense. The volume should be less than the original. I decrease the temperature. But there's always somebody that's going to say, I don't get the whole Kelvin thing. Because I can plug this in my calculator using 50 and 25. I can do that. Well, yeah, I mean, I can too. And so let's pretend that you plug this in with the Celsius temperatures. It actually looks like the temperature went down by half, right? Going from 50 degrees to 25 degrees. It looks like if you were to decrease the temperature by half, your volume should also decrease by half. Ooh. Okay, so if by accident you plugged this in using the Celsius temperatures, your V2 should be half of the original. Let's say 1.25. Okay, so I didn't go to like 2 sig figs, but whatever. It's not right anyways. And so there's always somebody that says, why isn't it 1.25? I can plug it in my calculator, so why isn't it? I mean, that's a pretty big difference. I feel for you. So obviously this is not right. It does not match lab data. That's the only way we know that you cannot use Celsius temperatures when you study gas laws. It just doesn't happen like that in the lab. And you can go in the lab and do this experiment. You could take a balloon, 2.5 liter balloon at 50 degrees, and cool it to 25 degrees, measure the new volume. It's not 1.25. It just doesn't go down by half. It goes down, but volume and temperature are only directly proportional when the temperature is measured in Kelvin, based on experimentation. The 2.3 matches what we experience in the lab. It matches the lab measurements. So we must do our calculations using Kelvin. Not a big deal, because I'm going to tell you the conversion between Celsius and Kelvin. You really just have to remember to do it. There's qualitative questions on the next test that might say A, B, C, D. If the Celsius temperature doubles, what happens to the volume? And one of the choices is like, does the volume go down? Which, I mean, if I double the temperature, I should be at least increasing the volume, right? If I increase the temperature, I should increase the volume. If the Celsius temperature doubles, the volume will not double. it'll increase, but not double. Now, if the question said that the Kelvin temperature doubles, then bingo, you got it. The volume will double. So you just have to watch the wording. If the Celsius temperature doubles, the volume will increase, but it will not double. Or kind of like this example. The Celsius temperature went down by half. Well, the volume goes down, but not by half. Not in the lab. Okay, so super easy. This helium one is even easier because the temperature is already in Kelvin. This is an insult to your intelligence. Plug and chug is what I love about gas laws. Helium occupies a volume of 3.8 liters at 95 Kelvin. There's my initial conditions already. At what temperature would the sample expand to 4 liters? 4 liters is my final volume. I want to know the temperature, T2. Okay, so you plug this in your calculator. Without a calculator, I can at least tell you that the volume is increasing slightly. So the Kelvin temperature must increase slightly. So I'm looking for something a little bit greater than 95. So if I plug this in my calculator, again, we just cross multiply. So I'm going 95 times 4 divided by 3.8. T2 is like 100. Boom, got it. There she is. So these gas laws are great. Qualitatively, we need to be able to explain this on a particle level. Why does the temperature need to increase? Because we need more kinetic energy so the particles can have more collisions. More collisions with the walls of an expandable container should increase the volume. And then quantitatively, I can use this simple equation to calculate the exact temperature needed in kelvins.